What's up guys, Major Math with another video on fluid mechanics. If you have any questions, drop it in the comments, and if you're having trouble with other problems, I've attached my email in the description, so please feel free to reach out. Without further ado, let's get started. Question or example 3.5 in the textbook says, what is the pressure of the air in the tank if L1 equals 40 centimeters, L2 is 100 centimeters, and L3 is 80 centimeters? Okay, so usually our first steps are to write the given and the goal, but this question is so short. I'm just going to say these are our givens, right? And our goal is to find the pressure at point 2. The pressure of the air in tank. So, to do this, we have to use the... we should write our assumptions first, huh? So, we're going to assume... So, the equation we have to use is going to require to know the specific weight. So to get our values from the textbook of the specific weight of the mercury in the air, we're going to have to assume a temperature. So assume a temperature of 20 degrees Celsius. We look in the textbook, we know that the specific weight of air at 20 degrees is 11.8. And that's newtons per meter cubed. And then we also know the mercury at 20 degrees Celsius has a specific weight of 133,000 newtons per meter cubed. Right. We need to know the specific weight of oil as well. It gives us a specific gravity. So let's go ahead and find that real quick because we're going to need that. If you guys remember, it's the same with density, but you can also do specific weight. The formula of specific gravity is the specific weight of the liquid divided by the specific weight of water at a temperature of 4 degrees Celsius. Let's rearrange this so that we're doing multiplying specific gravity by the specific weight of water at a 4 degree temperature of Celsius. Let's go ahead and plug those in. We know the specific weight is 0.8, and then we know that this value, specific weight of water at 4 degrees Celsius, is 9810 newtons per meter cubed. Put that in the calculator. Say that the specific weight of oil is 7850. Okay. So those are going to be important. The formula you use, this is called manometer, when you have these curved tubes and we're finding the pressure. We have to use the manometer equation. It says pressure 2 equals pressure 1 plus the summation, everything going downwards, to specific weight of that liquid times the height. And then you subtract the summation of everything going up. This is easier to explain once we just see it, instead of trying to explain the formula now. So we'll just go ahead and run through this. So notice I have pressure 2 and pressure 1. That correlates to these labeled numbers. So we're going to be starting at pressure 1, and we're trying to find pressure 2, right? The pressure of the air. So to do so, I want to say something too real quick. The textbook, it just assumes that air has a pressure of 0, just because it's so minuscule. If you look at the specific weight of air compared to mercury and even oil, it's just so much less that you can get away with assuming that it's 0. But for the lesson's sake, I'm going to use what the textbook says, but we'll get the exact same answer once you round, basically. So we're trying to go from pressure, we're finding pressure 2, and this is the formula. So let's go ahead and look at this. So we know we're looking at gauge, because in the textbook, if it doesn't say absolute, if the question doesn't specify absolute pressure, just always assume gauge. So we're finding the gauge. We know that pressure 1, so the pressure at this point is 0 gauge, because it's exposed to the atmosphere. Like, there's no pressure It's just the atmospheric pressure. So it's zero pressure gauge. So then we know to use this we have to do everything, whatever liquid we're in, we multiply that specific weight by the height going down, and we do that every time going down you add that up, and then every time going up you subtract it. So we'll see how that looks. We know that the specific weight of mercury, so that we're going down, so it's going to be positive, and we do specific weight of mercury times the height going down, which is L3. Then now we're going, so we're at this point, right? So we move down to this point, and remember that we can use the liquid interface rule. I think I've called it the planar interface rule as well. It says that when you're inside the same liquid with a constant density, that these 2 points, if you move horizontally or laterally, those 2 points will have the same exact pressure. We know, like, if we move down to this point, this pressure would be higher than this one because you're going deeper. But since we're just going horizontal, we know that the pressure is the exact same. This makes sense too because if you look at the pressure formula, which is a force over a given area, we can rearrange that and get that pressure equals specific weight times height or depth. So if we're inside the same liquid, so the specific weight's going to be the same, right, for mercury. And then if we're at the same height, the pressure is going to be the exact same. So you can use the definition of the liquid interface rule, or you can also just look back on this pressure rule and be like, that makes sense because we're in the same liquid, it's the same height, it's going to be the same exact pressure. So once we get to this point, we can move horizontally over and know that its pressures will be equal. Now we got to move up the height of L2 while in air. Since we're moving up, we're going to subtract, and then we're going to use the specific weight of air because that's what we're in now, and we're going to go up the distance of L2. And we're at this point, we know we can just move horizontally over to this point. Now we're going to move down again, and this time we're in the liquid oil. So we're going to move down this point by L1. So we got specific weight of oil times L1. Then once we're at this point, we know we can move horizontally over. It's in the same liquid, and then we get to point 2. So now we're at point 2. We don't have to do anything more. So now we just have to plug in all these values, which we are given all the L values, and then we just found all these specific weight values. So let's go ahead and plug all those in. L3, and then let's go ahead and convert these. So we want everything in meters because that's what the specific weight's in. So if you divide centimeters by 100, you will be able to convert them to meters. I think the textbook also assumes a value of 0, so that basically this pressure, it just says the pressure of the air in general. It doesn't give a specific point. So if you assume that the pressure is, or the specific weight is 0 with air, it's just basically assuming that the pressure within the air is all equal. So that's probably why the textbook did that as well, but it doesn't really matter. And then L1 is 0.4. Put that in the calculator. You'll get that, if you round it, put it in the calculator, you'll get 110,000 pascals. Now if you divide that by 1,000, you can convert it to kilopascals. So the pressure in the air at point 2 is 110 kilopascals. There you go. Thanks for watching, soldiers. Don't forget to leave a like and subscribe for more content like this. If you have any questions, leave it on the comments, and if you need help with any other problems, feel free to contact me with the email shown on the screen.